So actually we'll talk today about the transformers with external memory, and the talk was planned to be a little bit technical. So we can calibrate the technicality level of the talk even now. So raise your hand if you know what is the cross attention. Okay, we'll try not to do that a lot. So I have to mention that English is my second language, so if you didn't understand something or you just want to repeat something, just raise your hand and ask to do that, stand up. So yeah, here's the agenda. We will talk about external memory, what is the motivation was for researcher who decided to attach external memory to transformers, how it can be attached to transformers. There's a lot of different ways. Is it even scalable? And we will have a look on different modalities, so not only texts. So yeah, here's the problem. If you just query your LLM, your current LLMs like OpenAI, ChatGPT, GPT-4, which is even better, with some new questions, let's say, some up-to-date questions. For instance, who is the 2023 NBA MVP, so MVP for this year? The model will answer you, okay, I was trained before the 2021, so I don't know, so I don't have up-to-date information about that, and that's the problem. So what is the solution? To retrain a model like every year or half of the year, or what is the chunk of time that you want to retrain a model? And the simple answer was that, okay, we can use an external memory. Maybe some memory from the internet, maybe like RAM memory, maybe persistent memory or something, but we can use some memory bank that we can update somehow. But that's not the only intuition. So the first idea, like the first motivation I have read in articles about the external memory was that, okay, we lay down on the two things, that we think that the model itself, the large language model, can reason, obviously, and also it remembers the fact, a lot of facts. And the more model is, the more facts it knows, right? So we just think that the parameters of the models is correlated with the amount of like knowledge that model has. And we probably want to, let's say, turn this ability to something else, so maybe some external memory, and let the model itself, by trainable parameter, to learn to reason a little bit more, so that maybe for some knowledge-intensive tasks, we will use external memory and the model, which is like 10 times less parameters. Also, the external memory itself can help you with infinite simplicity, because for like obviously if you use less parameters for the models, it's faster and faster a lot. Also, it somehow resolve the problem of limited context window. Like obviously when we use transformer, we have a quadratic problem. So we have a quadratic complexity in terms of times for self-attention. So there is a problem. We can't grow our context window constantly. Also, if we retrieve some additional knowledge from external memory, we probably can store the source of the information that we got, so we can return to the user the source of information. And this ability of the model is like now using a lot in some APIs like ChatGPT and so on. So first, yeah, that's one that I mentioned, that model knowledge remains up to date, so we can ask the question about the nearest past. Also the data variety, or I would say knowledge variety, and actually the external memory usage, like to attach, to enhance your model with external memory, is pretty simple, and that's why everyone can use that. Okay, when I first think about external memory, I spot that lots of vector database startups are actively integrating with length chains, with llama index, and like some of application like that. And I will ask myself why. And one of the most usable, like one of the most frequently usable use case is that people just trying to update their prompt with external memory and feed it to the LLM, right? And that's like a really simple use case. But that is not the only way. So you can enhance your model with external memory in different parts of the transformer. So you can modify your self-attention. You can also do the probability shifting. So okay, and we will review some articles today, some of them, and they differ a lot in this space. So some of the models is augmenting the prompt by using external memory. Some of the models are trying to enhance the self-attention, so modify it somehow, and some of them just doing the probability shifting. And I think this one is older one. Okay, so what is retrieval and how we use that, how we use the external memory. So imagine we have some external key value memory. And for now, it's not necessary for us what is the keys and what is the values. But let's say for every single query that user write down to the LLM, we can compute the embedding and compare it with the keys. And you also can do it in different levels. So you can calculate the embedding for, let's say, query itself. So you can calculate the embedding for like the token representation, or maybe even some intermediate model representation, so some hidden states, and use external memory for that. So by encoding, I mean like lots of approaches uses work-like models or some encoder models or transformer encoder models, and mostly it's frozen, but sometimes it's trainable during the process of like pre-training external memory model. So yeah, you can compute the embedding, you can compare it with all of the keys, which is also some representations to have the key nearest neighbors keys and corresponding values. And after that, you somehow incorporate these values to your large language models or language models to get the response. Okay, and yeah, the retrieval itself can be realized in different ways. And there is, yes, few approaches. So yeah, as I mentioned, the parameters of the embedder is mostly frozen, but in some papers it's not. And yeah, in the architecture and folder, yeah, what is about the retrieval itself? So we can do that like in exact way. So we can like spot the most like similar object from the bank, but doing that in exact way means like probably quadratic complexity. So there is also alternatives which helps like modern resources scale external memory a lot. Is like approximate nearest neighbor search, which is sublinear. So MODM, which HNSW leap algorithm, and loss of realization, which I listed here. So yeah, base and so on. And U-search, which is our let's deep dive a little in some papers. So we will start with a simple approach, which is SPI-LM by DeepMind. That is the idea that we want to shift some logics. So what is that? Okay, so we have our external memory, which is internal representation of the model, like hidden state, and their corresponding tokens, which we can store during the pre-training process. So yeah, and they use the external memory bank like equal to the pre-training corpus. So all of the let's say input sequences that like go to the models after this stores somehow in external memory, and yeah, you can use it a little bit after. And they use gating mechanism to make a shift, logic shift. I will show in the image. So they also incorporate short-term memory, but we won't say a lot about that. But yeah, they use the transformer model, they use the sequence, they calculate the hidden state, right? To the they go to the forward pass by all of the model. They got the hidden from the last token, which is represent the context, and they spot the similar object from the key value store, which is long memory. They call for that. They retrieve the key nearest neighbors, aggregate them and use in the final probability calculation. Okay, what it brings to us? That's one of the first models with external memory itself. I think the first one is CAN-NLM, but this is also similar to that. It gives us the understanding that it works, first of all, and it works for language modeling and token modeling. Also, it says us that we can even train as a, let's say, external memory, some abstract memory, our training corpus. So we don't need to go to some other data sets, something like download some new data and so on and so forth, but we can use training corpus. Yeah, and in this article, it was an interesting thing that the number of retrieved neighbors, so the number of this K in KNN is not really affect the results. So we can actually gather only one neighbor and get the same results as the, okay, we will take 8 neighbors or 16 neighbors or something like that. Yeah, but there was a problem. So for each token, for each hidden state of the token, if you're doing the probability shifting, you need to retrieve K nearest neighbors. And as I already mentioned, they didn't use approximate nearest neighbor search, so they have the really like quadratic time complexity, so it takes so long to retrieve for every single token in training corpus a neighbor. So yeah, that is the question: should we do that? The second approach that I decided to absorb that is retrieval augmented generation by Facebook. Yeah, they already think that, okay, maybe finding key nearest neighbor for each token is time consuming. So let's say we will do that for the chunk of tokens. So yeah, they decided to encode chunks of 100 tokens, and they also managed to have these chunks encoded in their key value storage, and they did it with sentences forms, not just in verbal. It's like interactive pre-trained model, which can encode sentences, not only tokens. So yeah, they also decided, okay, what if we do train the query encoder? And I will show what is the query encoder later in the images. They also incorporate the approximate nearest neighbor search by phrase, which is faster, which is not quadratic, it's sublinear. And also, what they did, they just, and then they didn't the logit shift, they just decided, okay, we will retrieve the most similar document from our like pre-training corpus, and we will just prepend it in the prompt. So it's kind of a simple idea, but it works. Yeah, and as sentence coders, they take one of the sentence word models, which is contrasted with trained models. So yeah, here what you can see is that, yeah, they have for every single input sequence a query encoder. They encode it into the vector, and after that they retrieve the most similar documents, and they prepend to these documents in the prompt this input sequence in the end, and only after that they feed it into the generative model. So yeah, and they backpropagate end to end, so they even trying to train this query encoder, but their own ablation study said that it's not very, like, let's say, necessary. Okay, I will explain what they really trained during the training process. So they take one of the sentence transformers, which is contrastively pre-trained, and I'll explain what is that. So you're trying to have two sentences which is similar in some way, and you like decided that they are similar, and you feed it to the two different encoders. You're doing like sentence pooling, so you have for every single token the representation, and after that you want to like somehow aggregate that, so you have a pooling layer, and after that you just count the cosine similarity. And for similar sentences, you have like the ground truth is 1. For sentences which are not the pair itself, and yeah, like your negative is in batch negatives, you have to get a 0 score. Okay, so what they did, they just decided to do that. Okay, we will, during the training, this end-to-end training, we will only train this part, and we do not touch that. So the documents, embeddings and the representation are frozen, so it's very beneficial for external memory because you don't need to update that. What they prove in the paper that in context learning, which is preparing your query to some similar document in the prompt, is beneficial for language modeling and token modeling itself. They said, okay, we don't need to initialize our models with some noise or zeros or something, but we can initialize that with pre-trained models. So the model here is BERT model, one of them, I think, Unum L12 or something like that, and here is the bar. So the proof that it's possible for you can incorporate external model, external memory for some pre-trained model. Also, they show that lots of downstream tasks can benefit from external memory, and if you will think a little about that, it's something like knowledge-intensive tasks. The question after this paper for me personally was, okay, why don't you just train your retriever model end-to-end? And one of the papers, which I do not want to observe here, is called Real, and they decided to train, they do exactly the same, but they just train end-to-end whole retriever model, so both of these dollars. And they are, with some frequency, updating external memory, which is time-consuming, but it has a little bit better results. Okay, the next model, I think, is one of the most interesting one from DeepMind called Retro. Here's also the idea with chunking your input sequences is incorporated, and not only, but also for that they decided to enhance not on the prompt by external memory, not the light shift or something, but they decided, okay, we will update somehow the attention mechanism itself. So they enhance the model, the transformer block inside with a mechanism called chunk cross attention. I'll talk about it a little bit later, but without diving deep early. Also, they used approximate nearest neighbor retrieval based on their own library called Skynan, and it's really fast. So they decided to scale up external memory database, this huge memory bank, for 2 trillion of tokens, trillion of chunk tokens, which is a lot. And they also, I think, one of the first papers which decided to show us the scale ablation for the external memory. So the answer for the question okay, if we grow the number of parameters of the models, will external memory be still beneficial for the model or not? What if we grow not the number of parameters, but the number of tokens in the external memory will help that, and so on and so forth. All of such questions. Okay, their memory banks look like that. So they have BERT sentence embedding. I think they also incorporate some of the mini-LM or something from the BERT. And their values is an interesting thing. So they chunk sequences, I think for 64 tokens. Yeah, 64 tokens. And the value of this bank is not the chunk itself, but the chunk that goes after. And they also have the ablation, okay, what is better to take the value, the chunk itself or the neighbor, and they decided, okay, this doesn't really matter. Okay, there's the cross-tension mechanism, and I think I already did the left side image and the right side is a little complicated. I don't know, maybe we can. So they have a chunks for input sequence, and they retrieve the neighbor for every single chunk. So we have neighbors for every single chunk, some number of neighbors, k neighbors. And that retrieving process is completely frozen, so they didn't like propagate through that. So after that, after the first self-attention layer in our transformer block, what we do is we are trying to, with these neighbors, with this like just a chunk of tokens, we want to have the embedded this token. So what they did, they incorporate the second model. The first model is retrieval, let's say. The second is the attention itself, so the retro block. And the third one is this little transformer encoder, which is the cross attention is conditioned to the current tokens. So yeah, they got the neighbors encoding, and after that they got the cross attention to these neighbors for every single chunk that they have here. So like you can think about that as okay, for every single chunk you have some neighbor, some similar sentences or pieces of text in your bank, and you can attend to that. So you can make the conditional attention to that in your self-attention layer. Okay, so that's how they interpret external memory. There is the huge scalability ablation, which shows us a lot of information about external memory. The first, I think one of the most interesting is that they scaled the number of parameters of the model to like 7 billion models, and it's still beneficial to use external memory. So like the circles is external memory, and the triangles and axes, yeah, the models without that. Also, they show us that we can grow external memory bank, and it's still like beneficial to grow it. Like they incorporate 1 trillion tokens data set, and it still was beneficial for the model. What else? Yeah, the number of neighbors is not the obvious thing, because first with growing the number of neighbors, you get more, but like better results. But after some number is degrading, so it's kind of a tricky thing. Yeah, what else? Okay, that was just different evaluations, so you can see that for a lot of tasks, pre-training tasks and even downstream tasks, it's beneficial to use external memory. So yeah, what is the conclusions from the retro? I think they showed that chunking this input sequence and incorporating external memory into the self-attention or transformer block is beneficial, and you can avoid a lot of computation that you used to like compute before. Okay, yeah, and all these like games around, okay, should we keep frozen our retriever, or should we train it? Should it be differentiable or not? Okay, they answered like, okay, we can freeze it, and they in evaluation tried both, like freezing that and make it trainable, and their evaluation says, okay, it doesn't matter, it's better to keep it frozen, because like you don't need to update your external memory, and it's like way better. Yeah, and one more like benefit is that you can pre-compute that for whole training sentence before to start training itself. And yeah, and they show the first like research group that show us the scaling of relation to the external memory itself. I think the last interesting paper that I wanted to observe is memorizing transformer by Google Research. They also incorporate the same idea, but their keys and values is something different, because it is just key values from the attention. So they did the same idea, but their external memory is just first in, first out queue, which is nascent by the training process with keys and values of the attention. So I'll show you how it works. Yes, I think it's a simple one. Okay, yeah. So what they did like self-attention itself for the local context, and also for this context they retrieve the most similar keys by the queries from the local context, and they return the values. So they attend not only to the local context, but for this like huge first in first out queue, which is also scalable and scales ablations, is in the paper. But it's kind of a weird thing because the author itself in some podcast says that for me it's surprising that my updating state is way less than the window size. So there is a different model steps, so model representations of key and values in this view, but it's still working somehow. I think one of the most interesting insight from this paper from memorizing performer is that you don't need to pre-train your model with external memory. You just can incorporate that after pre-training with some kind of fine-tuning. So this ablation. So train for 6K training steps the model with memory, without, and after some 50K steps, they decided to fine-tune with external memory, and it works like the same way as pre-training with external memories. Yeah, that's one of the main insights here, I think. Okay, the short summary of the external memory in large language models is that okay, use approximately nearest neighbor, so because it's performance level is almost the same, it's almost the same neighbors, but you can reduce your time complexity a lot. The second one, that external memory can be beneficial for large language models and can reduce your number of parameters like 25x, according to the retro paper. Also, the model, memory transformers, transformed to external memory scales well with model size, with database size, and with number of neighbors. Yeah, this is the insight from the memory performer, that you don't need to train this external memory, you can just fine-tune for that. Yeah. But after that, in 2023, there was an interesting paper by NVIDIA, which decided, okay, the retro show us not that large, really large models, we will train the larger. So they did the ablation for the model size to, I think the scale is up to 10 billion parameters or something like that with external memory. And they decided to check, okay, for which downstream task it is beneficial to pre-train your model with external memory. And then it turns out, and it's kind of an obvious thing, that okay, knowledge-intensive task is beneficial from external memory, but everything else is not really. So if you're doing something, okay, question answering system, or maybe just chit chatting, or if you're just interacting with casual user who's just wanted to ask some simple questions, maybe talk a little, it's beneficial, but not for everything. So keep that in mind. Also, I was wanted to mention the different modalities, which is also can benefit from external memory. And the first one is computer vision, so images. So for instance, one of the papers that I found are trained with contrastive learning, and for contrastive learning, it's always beneficial to use external memory. First of all, you can mine the positive examples for your self-supervised data set. Second, you can mine the hard negatives. And just you can grow your global batch size in synthetic way, but just using external memory and not doing that. Okay, I can horizontally scale up with million GPUs. Yeah, and one more model by Google Research is also incorporate external memory in contrast with the training for multimodality, so text image understanding, which is I'm doing in my startup called Unum, and I also tried a lot to samples hard negatives and positive for in-batch contrastive learning, and it works well. So that is not only textual model that can benefit from external memory banks. So thank you for your attention. And
have you heard about Vladimir paper by Microsoft about scaling transformer to 1 billion?
Context window.
Yeah, context window.
I think we heard about, but I don't remember exactly. I think you can remember the abstract, but not the paper itself. What does it say?
It's basically proposes the dilated attention like mind maps or like hierarchical clustering.
So it's about the context window,
Yeah,
right?
yeah.
So see, there's like another like yeah, it's kind of a different approach. So growing your context window, it can be realized by the external memory, but not only. So with using external memory, for instance, in memorizing transformer, you can grow your context window just because you're chunking everything, and you do not attend for every single token in your input sequence, which is okay 2048, but you're attending only for the chunk, which is 64, for instance, and for external memory, and it's also just trimming your 64 tokens. So you can also grow your context window better.
Yeah,
But I think the approach is kind of different.
they propose something similar to that. My question was actually about is it what's your intuition about the context window size and external memory augmentation, like which will like rise better?
Yeah, look, what is the attention map in the self-attention? Is the huge quadratic matrix, which is sequence length, right? And here also. And you're just trying to compute this similarities, right? Scalable product. By using memorizing transform, for instance, you're chunking your sequence with chunks like 64, like length 64, and here is like, let's say, 2048. So you chunk 64 tokens, and you find some external 64 tokens which is similar, and you prepare it here. And you just twice do like your self-attention twice in this input chunk and the chunk from external memory, so that you don't need to compute. Let's say this is also 64 and 64. You don't need to compute all of that. See? So you already somehow solved your quadratic computational problem, okay, with self-attention, depending on the sequence length. So somehow it helps, but not I will say there is a lot of better approach to grow your context window than an external memory itself. So it's not the only way. Okay?
Can we extract the exact data from the one token? I mean, in each form the data contains in the...
No. I think you're asking about one of the model I mentioned. Maybe I mispronounced that, but it's not for the token, it's for the hidden state. But hidden state is the representation of your context, right? Of all of your left-sided context. So it's not neighbors for the token, it's for the context.
Okay.
So it's also hidden here. Anyone else?
Yeah, I have a question about this picture. So it's beneficial to use like more memory and
Yeah, sure. Here, there is the billion of tokens.
Yeah.
And
my question is, do they extend data set as well or not?
I think, yeah. So basically, this is a good question because in papers they said that they use the pre-training corpus. And as far as I know from NVIDIA paper, that the pre-training corpus was 300 billion, so not 2 trillion memory bank. But the paper state on that is 1 trillion tokens data set. So that was kind of confusing thing. But yeah, they proved that, okay, we can scale it up. And we can use training corpus, and also, I'm not sure is it retro or memorized from someone else. They prove that we can take some other data sets, let's say random Wikipedia, like huge dump, and attend to them, and it's also beneficial to the model.
My question is a bit out of the box, but it's used for multimodal systems, yes?
It can be, yeah.
My question is, can, for example, BERT-like models, retrieval models, be used for both digital and analog systems? For example, for neuromorphic computers, first step to AGI, because neuromorphic computers use both digital and analog thinking systems.
Okay, but BERT-like model is understanding model, so it's bidirectional, so it can see the context from both sides. So it's a model which is incorporated to somehow embed your input representation of sequence with the text in vector, right? So it's not going to generate with some new insights or produce some reasoning or stuff, etc. So maybe GPT-like models, yes, but BERT-like, I don't think so. It's understanding models. So it's just giving a vector.
How do you think with the future algorithmic improvements of some approaches like memorizing transformer, will companies like VV8 or Pinecone go bankrupt or not?
Actually, we are building the competing startup to the startup you mentioned. So I'm working for the startup called Unum, and we have the product called Research, which is implementation of HNSW, which is one of the fastest, I think. This is my humble opinion. But no, like alternatively, everyone should use it for, like not should, maybe will use it for their pre-training pipelines. So I think the use cases of vector database are growing for their like uniqueness. So yeah, not only to prepend in prompt, but somehow to incorporate in such complicated things as chunk cross attention as I already mentioned. So anyone else, guys, or coffee break?
What was your conclusions on memorizing transformers?
Oh, memorizing. Well, it's kind of an interesting thing because this thing was for me really confusing. So you store different training, different model training steps to keep their keys and values, which is like from different distribution and still works. So I want to say that they said in their conclusion that okay, we can scale this up like continuously, but it's not true. For instance, if you have like your keying values from the first step of training and from the last in the epoch, it will be like completely different things. And how can you like retrieve nearest neighbors from that and incorporate in training? I don't think it will scale as well. So one of the most interesting insights here is this, that you don't need to pre-train your model with external memory because it can bring you some computation complexity, right? But you can just fine-tune that. And it's interesting because I can take, like what they say directly, I can take right now Vicuna, like 180 billion parameters model, which was released like some few days ago, right? Huge model, and incorporate external memory for them, right? So that's what this paper said, and that's kind of an interesting thing.
Okay, sorry for taking your time from coffee break. Let's take it again.
Yeah, thank you guys.